Hello everyone, welcome back to our network security course. This week's topic is cryptographic hash functions and authentication. As you can see from the sections at the top, we are going to talk about hash functions, password cracking, message authentication codes, and authenticated encryption. Actually, all of these topics are somewhat independent, and in my applied cryptology course, I spent 1 week for each of these topics. So if you're interested, you can watch those videos too if you want to have more information about these topics. So they are different but not unrelated topics, but we have to start with hash functions, and then we will use these hash functions in all of these topics. So there are a lot of standards in all of these topics, so I have to cover all of them for our network security course so that the protocols that we are going to see in the future can make sense. So let's start. So hash function h is a keyless algorithm that takes a variable length input x and returns an output y of fixed length n. And this length is referred to as message digest length. So idea is simple. So you have a function. The input can be of any size, almost infinite, but the output size is always fixed. And nowadays we use like 256-bit output, but initial designs were as small as 128 bits. But this is a definition for a generic hash function. But in order for it to be a cryptographic hash function, we require it to have some special properties. And these properties called preimage resistance, second preimage resistance, and collision resistance. So in a minute, we will see what these topics are and why we need them. I will try to give a few examples why we need such properties. But we also want that a hash function to behave a random function. So the outputs should behave randomly. Actually, this property is required for instance, in many blockchain or cryptocurrency algorithms. For instance, the mining for Bitcoin actually relies on the fact that the output of SHA-256 hash function is somewhat random. So let's start with the first property, which we call preimage resistance. Given an output y, it should be hard to find any input x such that hx equals to y. So we have a function, we know it, we know the algorithm, and we are given an output, and we are asked to find any input that gives this output. So we want this problem to be hard. So a generic attack will require 2 to the n operations because the output size of y is n. So if you try 2 to the n different input, the size does not matter. The probability of hitting this y, the expected value of obtaining y becomes 1. So we say that this a generic attack will require this many options. So if you increase n, the attack becomes harder. So why do we need such a property? Actually, we need this property for a lot of different reasons. Let me give you an example in the case of password storing. So in a password file or in a database, one does not store the username and the password of the users directly, because if you do it and the file or the database leaks, all of the username and the passwords also leaks. And this is what happened in the 1990s and beginning of 2000s. But the problem is that people still don't know this, and people still are keeping the password as a plain text in the database. And almost every database leaks at least once in the history, so nobody can rely on this. And the problem is that, as I told you, a lot of people still keep passwords in this way in the database. And there is an easy way to check if somebody or a service or an application stores your password as a plain text. Just click on the I forgot my password button. And if they send back you your password with an email, then this means that your password is stored as a plain text, which is a very bad thing. But an easier solution would be, instead of storing the password in the database, just store the hash output of this password. So instead of storing x, just store y. Whenever you need to log in, it is still okay, because once you enter your password, the server takes hash of your password and check if it matches with the value that is stored in the database. And the good thing is that when the database leaks, the hackers would have Y, not the value X, so they cannot directly obtain your password. This is the good thing. So we can give a lot of different examples for this preimage resistance. For instance, even in cloud, almost every file stored with its hash value, so that we can check if it is a hash of a copyrighted file or not. I will mention this in a minute too. So this is important. So we don't store passwords directly. We have to store the hash, but this is just a basic example. It is still not okay to store passwords simply like this. I will mention why this is a bad idea in the topic of password cracking, but to be complete, let's say that you have to put a randomly generated value at the end of your password, which we call salt. And instead of taking the hash value of the whole thing, you have to take consecutively take the hash of this value thousands of times, and the result should be written to the database to be more secure. Again, we will have this topic when we're talking about password cracking. So let's move on. The second one is second preimage resistance. Given an output Y and input X1 such that the hash value of this X1 is Y. So we are given these values, X1 and Y. So at this point, it should be hard to find any other X2, which is different than X1, such that H of X2 also gives you Y. So you know X1, you know Y. You are trying to find X2 so that H of X2 also Y. So you might think that, is it possible? The answer is yes, this is always possible, because remember the definition of the H function. We said that input can have any size, but the output size is fixed. So from a very huge space, you are mapping elements to a very small space. So there will be a lot of collisions. Two different values will always go to the same Y value. So there are X2, maybe X3 and X4 that would also give this value Y, but it should be hard to obtain. So this is why we also will say that a generic attack would require around 2 to the n operations. Again, this n is the bit size of the value Y, which we also refer to as message digest length. An example is as follows. If you store the hashes of your files or the hash of your hard drive, which forensics actually does this, at a crime scene, you have to take hash of every storage. So assume that you've done this. If the attacker modifies the files, so for instance, puts a malicious code inside them or adds more files to the hard drive and so on, and can still obtain the same hash value Y, then the attacker can fool you. So at the court, they can give a different hard drive, which is different than the one at the crime scene, and claim that this was the hard drive at the crime scene. And this can be done, and unfortunately, if you use a bad hash function like MD5, which I observed that people are still using in Turkey, then this kind of things can happen. Okay, so you have to avoid some broken hash functions, which will be the topic of the next video. So let's move on. Let's move on to the third property that we require for a hash function to be called a cryptographic hash function. So we say that it should be hard to find any two inputs, x1 and x2, such that hx1 equals to hx2, which equals to some y value. So you might think that this is the same definition with the previous one, which we call second preimage resistance. But remember that in the second preimage resistance, we were given x1 and y value. We were trying to find x2. So we were given this x1 value. But in this case, we have more freedom. Only thing we know is the hash function h. So we are trying to come up with two inputs that will give us the same output. So we have more freedom here. For this reason, a generic attack requires a lot less operations. to be more precise, the square root of the previous one, which is 2 to the n over 2. So if n is 128 bits, as in the case of MD4 or MD5, then this would be 2 to the 64, which is achievable in today's computational power. And this result actually is due to a birthday paradox. This birthday paradox is somewhat famous and useful in crypto, but it is beyond the scope of this talk. So if you are interested why this is the case, again, you can look at my applied cryptology course videos. So why do we need such a property? Imagine the following situation. So assume that a hash function is not collision resistant. So you can always come up with x1 and x2 so that they have the same hash value. So a hacker can prepare two versions of a software driver for an operating system, where x1 is the correct driver and x2 contains a backdoor that allows access to the machine. So one is good and the other one has a Trojan in it. And the thing is that hash of both of the files are the same. If an hacker can do this, and in history we have seen examples of it, there was a malware that actually did this trick, flame malware. So if they can do this, what the hacker does is to send the X1 to operating system company for inspection. Since this has no malware in it, no backdoor, the operating system will say that, okay, this is a good driver, and they will sign it so that the operating system will think that this is a non-malicious file. But it is a cumbersome operation to sign a huge file. Nowadays, some drivers are gigabytes of data. For instance, NVIDIA drivers are always more than 1 gigabyte. So signing a 1 gigabyte file would take a lot of time, and the result would take more space than 1 gigabyte. So instead of signing the file, operating system company actually signs the hash of it with their private key. We haven't seen public key cryptography yet, but assume that people have private keys, they sign messages with this private key, and everybody else can use the public key to check if they signed it or not. So in this case, the operating system company signs the H of X1, where X1 has no malware in it, but the hacker now distributes X2. So they put this file to their web page, and people download it. When they try to install this drive, the operating system will check the H of this drive, which will be HX2, but it will be equal to HX1. And the operating system will think that, okay, I signed this file, so it is secure, and you can install it into your computer, and this way you get the virus. This is because HX1 equals to HX2, and the signature works. So we say that hash functions are Swiss Army knife of cryptography because they have many uses in cryptography, and some of them are digital signatures. An example I just gave. They are used in message authentication codes, which we will see soon. They can be used as pseudo-random number generators, and we need random number generators a lot in cryptography because many algorithms uses random numbers. It can be used in key derivation functions, which we'll also talk about. And they have a lot of many different uses. Especially it is used for the fact that you can represent a very huge file with a small output like this hash. And this is what happens in cloud systems. For instance, if you upload a movie file to your Dropbox account, which is like 5 gigabytes, and it is copyrighted material, when you try to upload it, you will also send the hash of your file, and the Dropbox will look at the blacklist and will realize that this is a copyrighted file, and they will not allow you to put it into your Dropbox folder. And again, in almost every cloud system stores a file only once. So if 1,000 people who don't know each other download the same file from the internet and put it into their Dropbox folder. Dropbox will store only one of them instead of 1,000 of them, because it will check the hash of the file and will realize that it already is stored in their data storage. So when the first person uploads it, Dropbox stores it and also takes the hash of it. And when the other people try to upload the same file to their Dropbox folder, Dropbox will say that I already have this file, so I will just simply store only one of them. So it is a good thing. So we have seen the main idea behind hash functions, but the question is, how can we define such a hash function? So there are two famous construction methods. Earlier versions, almost all of them use Merkle-Damgard construction. But nowadays we are seeing sponge constructions. So let's start with the Merkle-Damgard construction. So assume that you have a message. So this is maybe a file on your computer and you want to take the hash of it. So you divide it into blocks, and the block size actually depends on the f function that you are going to define. In this case, it is called the compression function. So idea is as follows. Start with an initialization vector and design a compression function which takes two inputs. So initially you take the initialization vector and the first block of the message. So if the message is long, if you have second block, then take the output of this compression function and put it as if it is the IV here. In this case, it is H1. Take the second block, continue in this way until you use all of the message blocks. And now here you produce the output, which is always fixed size, right? So a Merkle-Damgard construction is, the idea is this. Of course, how you define this compression function f depends on your choice. And in literature, we have a lot of examples, MD4, MD5, SHA-1, SHA-2, and we are going to see them in the next video. But almost all of the algorithms I mentioned so far are broken, except SHA-2. So for this reason, NIST thought that they should have the competition to have another hash function. And the winner of that competition was Ketchak algorithm, which is now referred to as SHA-3. And unlike these previous algorithms, Ketchak was a sponge function. So let's see how a sponge function is defined and how it can be used as a hash function. So a sponge function actually has a very huge internal state. It can be thousands of bits. And here you actually choose two parameters, rate and capacity, referred to as R bits and C bits in this picture. So you design a f function, which is a permutation actually. It can be operations like a block cipher having substitution and permutation layers. The choice is yours. But the idea is as follows. If your rate is R bits, you take the first R bit of your message, XOR it with the initial state, and perform this f function. And the output is again XORed with the second R bits of your message. So you keep doing this until the message ends. So the message length actually is divided with R to obtain those blocks. So they are fed into this state. So this is why we call it an absorbing phase. So imagine it as a sponge and you are actually filling it water here. So when the message is finished, now what you are going to do is to provide output. So first R bits again is produced as the output. If you want your output to be, for instance, 3 R bits, what you're going to do is to produce first R bits, then perform the F function again produce R bits, perform the F function again, and produce the next R bits. So here you just assume that we are squeezing the sponge and some water spills out, which is Z ice in this case. So again, this is the general picture. The choice of F actually defines your hash function. And again, Ketchak algorithm, which is now referred to as SHA-3, is a sponge construction like this. So in the next video, I will give you concrete examples for Merkle-Damgard construction and sponge construction by talking about MD4, MD5, SHA-1, SHA-2, and SHA-3.